Hello there and welcome to this impromptu video looking at the Component 2 A2 Computer Science exam, which is on the Monday the 19th of June in the morning, people. So this is different to the PM exam. We're in the morning now, so it'll start at 9 AM. Make sure you're up and early and make sure you are on time for your exam and prepare. Don't rush in there last minute because it'll set you off. All right. Now, we're going to talk through quite a lot of things here, and a lot of students have been in touch and told me what they want me to do, which I'm perfectly happy to go through. So all the things in yellow have been sent through to me, and that's what people want me to cover. In addition to some of that stuff, we've got things like hub switches and routers, little man questions, or little man computer, which is assembly language questions. We've got a bit of cryptography as well, and so on and so forth. So I'm going to start this off. Everything will be chapterized in the video itself, and we'll see how much we can get through. All right. So we'll start off with our 2.1, which is hardware and communication. So these are all things that we'd cover from the specification in chapter 2.1. We've got contemporary computer architecture, the fetch, decode, execute cycle, which was quite popular. A lot of people wanted me to go through the fetch, decode, execute cycle. Then we've got assembly language programming, which puts a lot of people off, but once you get your head around it, it's not actually that bad. And a couple of things to think about for the exam, some things that we just gloss over and we don't really spend much time on. Things like your wired network connection and your wireless network connections, because that contains a lot of hardware and we need to think about that for our exam. So the first thing to think about is that diagram there. You have to draw that in the exam potentially, and you will have to use those shapes. So you've got the ALU, the arithmetic logic unit, which is dealing with all of the floating point numbers. So integer division, whole logic operations, things like that. Comparison tests like greater than or less than. You've also got registers, and registers are small blocks of memory that we use, and you've got lots of different types of registers, but special registers, which are reserved for certain tasks, and you've got general purpose registers as well. Inside the control unit's job is really to execute the machine code by sending control signals across the motherboard around the rest of the computer, and the control signals are all sent via the control bus. And you might talk to things like the graphics cards or the hard drives and stuff like that, and it's part of the CPU's job to synchronize the instructions by using the processor's internal clock. And that keeps everything in the right rhythm, and sometimes it gets jumbled up and we have to start again. But the CPU in its entirety is the brain of the computer. It does everything that we need to do. We have input and output devices on either side as well of this diagram. Input devices, they can be peripheral like input devices, things like keyboards, and you've got output devices as well, like visual display units or a printer, for example. Then we've got memory in there. We're talking primary memory, which is our random access memory, and that's how we transfer data backwards and forwards from registers into the CPU. And there's a little summary for you as well. In case you're interested, you can pause the video there and have a look at a little summary of the job roles of those things inside the CPU. We've got our registers, and you might have heard of some of these registers before. We've got our program counter, which keeps track of everything and makes sure that the programs are pointing, we're pointing to the right instruction that we need to do, and it keeps things in order. We've also got the memory address register and the memory data register. So the MAR contains the address of the instruction or data that needs to be fetched. And our data register, the fetched instruction or data is stored in the MDR, because fetching instructions from memory can be a slow process. The processor always tries to fetch one instruction ahead of the one it's currently working on, and that's also known as pipelining. We also have the current instruction register, which, if you think about it, current instruction register. So once an instruction has been fetched, it is copied into the current instruction register for decoding and then further execution later on. Now, as the instruction in the CIR is being decoded and executed, the next instruction is being fetched into the memory data register. And again, that's that pipelining process that I was talking about. And then finally, we've got our accumulator or the ACC. So the accumulator, any instructions that are performed a part of the calculation that we're doing on the CPU at the time, makes use of the accumulator, and also the program counter makes use of the accumulator as well because it increments by 1, moving on to the next instruction. And there you go, there's your little summary again. And now we're going to talk about the fetch, decode, execute cycle. So how does it start from random access memory, get all the way through to being executed? Now, fetch, decode, execute are the stages that we go through. And this is the diagram that I use and I always talk about. So we've got the program counter, which points to the first instruction. That then gets passed over, the instruction memory address gets passed into the memory address register. The memory address register then will navigate to wherever that lives and then pass over whatever the contents is in RAM over into the memory data register. And that process of handing over allows the data register to do its thing, and it allows the address register to take the next address, and that speeds up our process a little bit. Then, once the memory address register passes its data into the memory data register, we increment the program counter by 1 to make sure that we're moving on to the next instruction. Once we have the data from the mailbox in random access memory, we pass it over to the current instruction register, and then once it's in the current instruction register, it's going to try and understand what those commands are. And then it's all about understanding and decoding at this stage. And then after that, once we know what the instructions are, once we've decoded it, we then pass over to the control unit, which sends the control signals around the motherboard and around the computer, actioning things like saving, loading, fetching more data, or displaying to the screen, something like that. So they're the stages that you need to think about, and that diagram's really powerful. As long as you can explain each step, you should be absolutely fine. Average mark for them kind of questions is 4 to 6, so bear that in mind. And then we've got the processor, which we talked about, and there's a little definition that you might want to learn. So the speed of a computer processor or CPU is determined by the clock cycle, and the clock cycle is the time taken between 2 pulses of an oscillator. The faster that happens, the faster your processor, and that's why we have different levels of processor from core i3, i5, i9, i11, whatever. That's why we have different stages of our processor. Some are much more expensive because they perform that job faster. Now, what happens if the processor is too slow getting data from random access memory over to our processor, or even fetching it all the way from secondary storage? That is called the bottleneck. The bottleneck is when your processor's action really, really quickly, getting everything done, and it's waiting. It's idle, waiting for more data. It's a very hungry thing, the processor, and then when you're trying to pass data over, it can slow down, massively slow down your computer if it's waiting for data to come in. Now, we need to fix this bottleneck, and we do that by using cache memory. And cache memory is another type of primary memory, and it's much faster than random access memory. But in addition to that, it is also much more expensive. It is small sized, it is volatile, which means if you switch your computer off, the power is lost to the cache memory and it loses its data. It also provides a high-speed data access to the processor, and it stores frequently used programs, applications, and data. Now, you need to think there, sometimes when we move between our secondary storage device on the right-hand side into random access memory, and then random access memory to cache memory there, the second image, and then over to our processor. So that allows us to trickle the data into the CPU and feed it a constant supply. Sometimes that doesn't happen because the transfer speed in our secondary storage device is much slower than our transfer speed in our cache memory. So sometimes we can have the bottleneck continue. Now, if the processor requests data and it's not inside cache and the data's not inside cache, then we have to go to random access memory, and then we say, is the data we're looking for inside random access memory? If it's not, then we have to go to secondary storage now, and that slows us down. So that's called a cache hit or a cache miss. If the processor requests data and it's in the cache, then it's a cache hit. If it's not in cache and it has to go to random access memory, that's called a cache miss. And you've got different levels of cache. So cache level 1 is extremely fast, quite small, and also it's very expensive. It's embedded into the CPU, so it's directly next to it to speed that transfer process up by physically not traveling that far. Level 2 is a higher capacity than level 1, but it does operate more slowly. Right? It might be located on the CPU, dedicated to a single core or a pair of cores, or located on a separate chip. Then you've got level 3 cache there, which works to improve the performance of level 1 and level 2 cache, and it's normally the highest capacity cache memory, but it does have a slower transfer rate than level 1 and level 2, but it's faster than random access memory. Okay, so there you've got a purpose of the summary of the different parts that we use in our fetch, decode, execute cycle and across our wider computer. And there's a couple of things that you need to be aware of. Cache memory improves system performance, but it's not essential. You don't need it. And you got to think about what else in regards to our primary storage. We have something called ROM as well. And ROM, read-only memory, it stores the programs required when the system boots up. It usually checks that all the hardware is functioning correctly. And it has something called a BIOS, a basic input-output system. And that stores system configurations and information, including the boot order. So what order we're going to boot up our computer, load the operating system, etc., and set up the storage devices so that we can load the operating system and allow you to get on. And when I first had my computer, it used to take 25 minutes to actually boot up. Nowadays, it's just seconds. It's crazy how far we've come. So, now we talk about the parallel processor. And the parallel processor is when you split or have two or more processors working together to perform a single task. And the tasks that are split up into smaller subtasks are known as threads. And these tasks are executed simultaneously or at the same time by all available processors, and any task can be processed by any processor. But just remember that when you do that, sometimes you can process things earlier than they are supposed to be processed, and some things get processed later than they're supposed to be processed, and you get these weird concurrent errors or bugs that occur from that process. But if we can split up our program, then it will decrease the time taken to execute a program. But you need specialist skills to write these things directly for the cores, and you have to really think hard about efficiency. So there's a lot of additional complexity when you're trying to use parallel processing, and every computer nowadays has more than one core. So when each separate core or processor has completed its own task, the results from all the cores need to be combined, and that can cause some issues, like I said before. So you've got some advantages there and some disadvantages of parallel processing. It's difficult to write programs. Results can come in different orders. Not all tasks can be split, so you have a serial part of your program which must remain together, and some parts can be parallelized or split up. Concurrency, or things running at the same time, can introduce a new class of software bugs that are really difficult to actually test for. But some of the advantages in that more instructions can be processed in a shorter time because they're executed simultaneously, and you can make use of lots more processors if needed. Now you might have seen for A2 we have something called Amdahl's law, and in the exam you might be expected to explain the limiting factors of parallelization in parallel processing in terms of runtime, so how long it takes to actually execute a program. Programs written specifically for parallel processing may have certain portions of the code that cannot be parallelized, so it can't be split. So now we've got the exam board Amdahl's law on the left hand side and the one from the textbook. The exam board one is slightly less confusing, I suppose. So you can say, let me just get my marker here, let me get my laser pointer. So you can say that the total processing time, that's the serial part and the parallel part. So that total time is calculated as follows. So the time taken for a single processor, then you've got the fraction of processing time plus the fraction which can be run in parallel divided by the number of processors that your computer has got. Like so, a quad-core processor, for example, then that would be 4. The fraction which can be run in parallel, so let's say it's 20%, for example, that would be 0.2. That can be run in parallel, and you put those numbers in, and the fraction of the processing, so if that one's 0.2, so 20% can be parallelized, then that would be 0.8 in there. Okay, these two numbers together should make 100%. All right. Now, if you're interested in running an example, here's a scenario that I put together for you. It says, when using a single core processor, a program has a runtime of 5 hours. So that's one single core takes 5 hours. If 60% or 3 hours of that program can be split up and spread across multiple cores, the minimum runtime cannot be less than the time taken to execute the non-parallelized, so the 40% that can't be split up across cores anymore. It can't be less than that, can it? Because that can't be split up, therefore it must be that time or greater than that time. Can't be less than it. So it's going to take 2 hours no matter how far you split up. If you had 1 million processors, it doesn't matter. It's still going to take 2 hours as a minimum. The remaining 40% will still need to be processed sequentially. So use Amdahl's law and show your working out of the runtime needed for 1 thread, and then do the same thing but for 4 threads. And the runtime of the executing program cannot be less than 2 hours, because that's the serial part of the program. So here we've got our example. You can see here we've got 5, which is the total time to take for running on a single core. We've got our 40%, which is our non-parallelized part, or the part that's serial and cannot be split up. Then you've got 1/1 is the number of processors, so this is single core, so 1/1 is single core. And then you've got the whole program, so 100% of the program, minus 0.4, and this is 0.6. So 0.4 is serial and cannot be split up. 0.6 is able to be parallelized and split up. And that then works out to our 5 hour total. Okay, if you bring in a quad core system or 4 cores, you're saying now the total time for 4 cores is 5 hours on a single core, 40% is serial and cannot be split. This time you've got 4 cores here, so 1/4 is 4 cores, and then you've got 0.6 which can be parallelized. And if you put all that in a calculator, which you're allowed in the exam, it will come out at 2.75 hours, which is 2 hours and 45 minutes. All right. So if you need more time, pause the video, go through that, get a pen and paper, write some stuff down there, and try and plug it into Amdahl's law. Right. It's a measurement of how much the runtime will be for different cores. And then we talk about assembly language. Now this puts a lot of people off. But assembly language is essentially just programming in its basic form. And you will get these commands in your exam questions. There's no need to remember these. You've got opcodes, which start with 1, 2, 3, 5, 6, 7, 8, 901 and 902. These are classic commands, 901 and 902. 901 is for input, requested from the user, and 902 is an output. Everything else, so add, subtract, store, load, branch, branch, branch. These are the starting opcodes, and then you have these X's, you'd replace those for your memory address location, okay, the number of your mailbox. And add adds a number, subtracts a number, stores a number, loads a number, line number to jump to. You will also get a description in the exam. That's what we've seen in exam questions. Now these questions do pop up in things like this. It says, explain the sequence of operations which will occur during the fetch phase of the fetch execute cycle, making clear the role of the program counter, the memory address register, and the memory data register. So let's have a go at this question. Just need to grab my pen. There we go. Right then, let's see if we can do this one then. Now this 3 marker, it's asking you to basically explain what's going on in the fetch phase of the fetch decode execute cycle. Now, if you remember from a diagram before, the address of the next instruction is copied from the program counter to the memory address register. So the contents of the program counter is passed into the memory address register. And you'd explain that using a sentence. The instruction from the memory address register, so the memory address register, the contents of that, the square brackets denote the contents. That, it's doing this thing again. That goes to the memory data register. Okay, memory data register. So the contents of the memory address register is passed into the memory data register. Then after that, don't forget that you have to then increment the program counter. So the contents of the program counter, or the instruction, is incremented. Try again. Is incremented by 1. So PC plus 1. Okay, there's your 3 marks for 3 clear instructions there. PC to MAR, MAR to MDR, PC equals PC plus 1. Okay, increment that one. The second one there, a simple computer has a number of 16-bit registers. Its assembly language set includes the following: load R, X, STOR, store, R, X, XOR, R1, R2. So it tells you what it does. Load RX, loads register R with the contents of address X. Store RX, stores contents of register R in address X. And XOR R1, R2 executes a bitwise XOR operation on the contents of register R1 and R2, storing the results in register R1. Explain what the following fragment of code does by showing the contents of the registers and addresses at each step. Make clear the contents of register 1 when the fragment has finished execution. Now I'm going to need a little bit more space for this, so let's just move that over there. Okay, now then, we've got 2 registers. We've got D1 initially contains those 16-bit numbers there, and D2 contains those ones. So all we're going to do now is show what's happening with these over here. Don't know why I just scatterballed those out there. It's very temperamental. I'll just move that wire. There we go. Okay. So we've got the original values, and I'll use those original values. And the first thing I'm going to do is I'm going to say what's happening to register 1. So load register 1, load R, so load register 1. I'll put a 1 there for register 1. I'm trying to do this without bringing up that second menu again. And then we've got to load it with the contents of address X. So what's D1? D1 is 1 0 0 1 0 1 1 0 1. Oh, it's being silly. There we go. So I've put the contents of that register in there now. And then I move to the second one, load 2. So load register 2. So I'll put 2 there. Load register 2 with the contents of D2. So 1 1 1 0 1 0 1 1 1 0 1 0. Oh, come on. 0 0 1 1. Okay. Now, done that. So finished and finished. XOR 1 and 2. So XOR, it says, executes a bitwise XOR operation. So if you don't remember what an XOR is, we do this in our logic operations. So we've got, let's say, A and B, 0 0 0 1 1 0 1 1. XOR them together. Why does it keep bringing up that? That's so annoying. Let's see if I can sort that out. So when you XOR these together, you've got zeros, you've got 1, you've got 1, and you've got 0. Okay? XOR works when you've got opposites. So I go along there and I'll write the opposites out, and you're going to store, does it say what you do with the contents of those? Executes bitwise, contents for register 1. Storing the results in register 1. So I'll say R1. What is the result of an XOR on those? It's going to be just a 1, so that's going to be, just need to make sure, because it's written not in the same line, so I need to make sure I'm accurate with this. So that's going to be 0, 1, 1, 1, 1, 1, 0, 1. And that's going to be 0, 1, 0, 0. And then okay, 4 opposites, so it's that 1, 1, 1, 1. I think that's right. People can correct me if I'm wrong in the comments, but I think that's right. Okay. Then what we've done, now we've done that, we've stored it, contents back in register 1. We're going to store 1 D3. So store R, so we're going to store register 1 in address X, so D3. That means we're going to copy what we've just done in this thing D3. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 13, 14, 15, 16. So 16, that gets copied into D3. And then finally, done that, then we XOR 1 and 2 together and see what we get. So when you register X and 1 together, when you XOR them together and store the contents in register 1, that means R1's going to come back, R1 comes back, and we put that in, and that's going to be the result of these again. So you've got register 1. One, 0, 0, 1. Very easy to make a mistake here, people. So be very, very careful in your exam. There is 3 ones there and a 0. 1, 1, 0, 0. So there's a 1 there and a 0. Now I probably should have done put R's on them as well, because they're register 1s, register 2s. We're using, don't forget we're using this one there, and we're XORing it with that one there. All right, that's what gives us this one. And that's it. So as long as you follow that, 4 marks in there, just tick that last one off, 4 marks in there. Just be careful not to make any mistakes. Skills needed, you just need to know what an XOR is and you're good to go. So that's one type of assembly language question. The other one, that's the mark scheme there for you in case you are interested in looking at that. It looks like we got that correct, I think. Yes, I think we did. I think we got it right. Next thing to look at is a question like this though. Okay, this is an assembly language question and it says a certain computer has an 8-bit accumulator with the following data stored in memory. Memory location 1A holds a star. Now, one thing I would say do is see if you can get hold of a bit of paper or just write on the booklet somewhere or whatever. Whatever's in front of you is yours, so you can write on the question booklet if needed. They can't tell you anything about that. So let's... Okay, I had a little bit of a pen malfunction there, so I think I fixed the problem now. Now, what we need is, on our piece of paper, we're going to have boxes like this, and it's going to contain information. So 1B, 1C, 1D, don't have to be pretty, one direction, and then we've got 20, whatever needs to be stored, 20 to 2F, right, or 20 should I say, because they look like base 16 numbers to me, 20 to 2F in there, and they are all variable storage. So we've got boxes in between them. If you think about it, 20, 21, 22, all that, right? And that is for variable storage. So store whatever you want in there. Now the computer's assembly language instruction set contains the following commands: load, JGT, which is jump to a label, add, STA, so store, jump again to label if the contents of the accumulator are greater than 0, greater than or equal to 0, should I say, output, and then decrement and clear. Okay, now it says, using only the assembly language commands shown above, write a program to produce the pattern shown above. Now inside these, we know we've got characters like the asterisk character in there, we've got the we've got a 5, we've got a 1 in 1C, and it holds a new line character, new line, I don't know, that could be like /n or something, like a new line, and then nothing in there. Okay, so we need to build this thing down here, which looks like 5 asterisks, and then it starts a new line and does another 5, new line, does another 5, new line, does another 5, new line. Okay, so I need to call for this 5 times, call the new line character, but I need some kind of loop. And for looping, we're going to be jumping to different labels. All right. Now, the first thing I always do when I do assembly language is I clear the instruction register, clear it, get it out of the way. All right. Just move this microphone over here so that people can hear me, because I'm looking at another screen while I'm writing this. Okay. So clear first, and then what we're going to do is we're going to load 1B into our, so LDA loads the accumulator with the content. So if I think about it, I'm going to put an accumulator, little box there. I'm going to load 5 in, okay? So to do that command, LDA, and then where's 5? It's in 1B, so load 1B. Next, I'm going to take that and store a copy of it in box 20. And why am I going to do that? Because I'm going to start decrementing 5 down to 4, down to 3, down to 2, down to 1. And every decrement of this, I'm going to produce an asterisk on the same line each time. This is my plan, people. I'm going to do that. Whether it works or not, I'll let you know. All right? Oh, it's doing that thing. Don't start with me now, pen. All right? We're going to do that. And then once we reach 0, I'm going to do a jump command if we've reached 0 and go back up to a label that I'm going to create. So I'm going to store that in 20. And if we look at the structure of our stars, think about it like in rows, and we've got columns of 5. Next row, column of 5. Next row, column of 5. So in order to do that, I'm going to then basically, I've stored that now in the accumulator, I'm going to load 1B. Now, you might think, what are you doing? Load 1B again. Right, do that. And now 5 is already in the accumulator, so that won't do anything in this stage here, or at this stage. And the next thing to do is store that in 21. So there's going to be a box now called 21. It's also going to hold the value in there. And then we're going to output 1A. So produce the star. We're going to load LDA 21. And then we're going to dec 1C. Okay, let's have a look at why we're doing that, right? So this here, when we load and we store, load 20, so we load 5 in, then we're going to LDA 1B, that's in there, store 21, so we store the contents of the accumulator in 21. That's fine then, yeah, okay, and then we output that and decrement by 1. So we output the star here. So this is just for us to see, by the way, that's a star. So we output the star there, we load 21 in again, and then we decrement, so we minus 1 from 5 on that line there. Now once we've decremented the number, we need to store that, because we always store our values back where we need them to be stored. Store. And then if we do that, we're going to jump to the label if the contents of the accumulator are greater than 0. Jump to the label, the contents of the accumulator are greater than or equal to 0. Right, so if I keep decrementing 5, 4, 3, 2, 1, if the contents of that accumulator in there is greater than 0, then I need to produce another star. So I'm going to jump up to wherever I need to output a star again, and that's this one here. So each star is in the column, so I might put col on this side here with a semicolon. That's how you denote a label. So I'll say jump to col. And it was clear in the mock exam that people were getting confused with the label. They just put JGT label. That wants you to create your own custom label. It doesn't want you to write label. So I've got col there, and col, that's for a column. So that means I will produce there, and then I would load it, and then I'll decrement by 1. So 5, 4, 3, 2, 1. And then once I've got to that stage there, I go to 0, and then I would skip past the column if I get to 0. So I'll produce 5 stars and then skip on past the column. And at this stage now, you need to output, so you need to load into the accumulator 20. Now why have I got 2 5s in here? Now this set of 5 here is for my columns, and this set of 5 here is for my rows. If you look, you can see I've got 5 stars followed by 5 rows of 5 stars. So I've got 5 from 5 and 5, 5 for the rows and 5 for the columns. So I need to do the same thing now that I did before. I decrement not 21 this time, but 20, because I take a row off. So once I've produced 5 stars and we get to 0, load what's in 20, decrement it by 1, so the rows goes down by 1, and then don't forget that we need to produce the new line. Okay, so that means once you've decremented it, make sure you store it back in box 20, and then you'd output 1D to give me a new line. And then you say, right, well, once you've outputted the new line, you need to then go back above all this column business, because you're starting again. So where would the row be? And that's what you got to think about. Load 1B, so we load 5. We then store 5 in 20. That's the precursor for these two. And then we load 1B. So this is where I would put row, because we're going to load 1B into the accumulator to start the countdown of the columns, and that's where that starts there, countdown of the columns. And then you carry on with yourself and output your 5 stars again. Then once you've output your 5 stars, decrement your rows, output your new line, and then jump again. So once I've done that 1D, I will JGT, and this time I'm going to JGT the row. And then at the end, once I've finished, I might clear it as well. But just remember, this is how you use labels, and this is as complex as it's going to get. Why have they put JGE in there? Well, that might be a red herring just to fool you, but just bear that in mind going forward. So taking this from the top, load 5 into the accumulator, store 5 in box 20, load 5 again into the accumulator if it's not already there, store that in 21. So you've populated your row box, you've populated your column box, then output 1A, so output your star, load whatever's in 21 into the accumulator and decrement it by 1, store it back in 21, keep going until you reach a value that is still greater than 0. If it's still greater than 0, go back to the column and run it again, go back to the column, run it again, go back to the column, run it again until you reach 0. Once you've reached 0, load 20, decrement the 20, so decrement the rows, and then store that back in 20, and then new line please, and keep going until the accumulator is less than 0. So you've got to keep going. And that'll produce 5 stars and then new lines and 5 rows. And that's it for 6 marks. Can be quite tricky, but you just have to get your head around it by practicing. There's lots of questions on our Google sites on these. So just remember where you're getting your marks from. You'll get your marks for outputting a new line character and a star. So that's a joint mark for those two, new lines and stars. Your inner loop for printing the stars. So that's where the col is there. You'll get 1 mark for that. You'll get 1 mark for the correct number of columns. So 5 columns, 5 rows. You get 1 mark for, and then the correct working solution will get you final mark. So if it's almost there but it doesn't work, you're going to get 1 mark less potentially. All right, and that's assembly language in there. And that looks good to me, but there's the mark scheme. If you need to pause it and have a look, by all means. And there's another question for you to have a go at there, very similar to the one we did before, but I'll leave that one on screen for you for a second. These slides are going out, by the way, so you can check the mark schemes as well. I'll put them in the slides for you, which are there. All right. Now, what I did get asked about as well, not input and output devices, didn't get asked about those, but just make sure you recap what your OCR is, optical character recognition, scanning text and converting it into digital. You've got OMR, which is optical mark recognition, that's scanning things like registers. Predetermined forms need to be created and all that sort of stuff. And that's what, you might remember those from school, especially primary school, I do. And then you've got MICR as well, which is magnetic ink character recognition. And we're defunct now, really. I mean, we used to use them for checks because the checks contained iron oxide ink, and that was easy to read. But the readers are very expensive for magnetic ink. Then you've got resistive and capacitive screens on there. There's some information about resistive screens and capacitive, but nobody asked about those. So I'll just skip right on. Voice input. So voice input are commands. Vocabulary dictation is when you dictate, and then the phone would like type what you've spoken, which people use quite a lot nowadays. And there's a number of advantages and disadvantages to using those. Background noise, accents, all that sort of stuff. It's very difficult, but it's also good for people with disabilities or repetitive strain injury, RSI, things like that. You can also have voice print recognition as well. And banks use that nowadays and things like that, store passwords. You've got contemporary storage devices, which starts to go off on a tangent really, away from the OCR, MICR and stuff like that. You've got hard disk drives, so you need to know the properties of hard disk drives, the fact that this physical movement, platters spinning, that kind of stuff. You've got solid state in addition to that. So solid state, what's good about solid state? Well, it's more durable because it doesn't have moving parts. It is more expensive, but it has electronically erasable, programmable read-only memory, which is much faster because we're transferring by the speed of electricity rather than physical movement. Flash storage, optical drives, that includes Blu-ray as well, Blu-ray discs. And don't forget, you might get asked about defragmentation and fragmentation. That only occurs in solid state drives, not solid state drives, sorry, hard disk drives. What am I talking about? Hard disk drives suffer from fragmentation over time. That's when things get deleted off your disk and then it has to be realigned later on. Okay, SSD cannot be defragmented because it uses solid state or direct access memory, okay, or NAND flash memory, let's say. Okay. And there's a typical exam question. I mean, it's old school floppy disk drives. Don't really see them anymore at all, which is a shame. And then there's the mark scheme to that question. If you wanted to pause the video, and there are more like that. There's loads more questions as well. And there's the mark scheme for it. Feel free to have a go at those, but they're all on our Google site. Now, bolted on to this topic, which is strange, is networks. And some people ask me to cover networks, so I will plough on and go through this for you. But What is the difference between the World Wide Web and the internet? Well, think of the internet as the physical and the World Wide Web as the non-physical or the digital. So World Wide Web is the hyperlinks and the internet is the physical network. And there's a little map of the internet. It's much, 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 much bigger than that. But every device that's linked to the internet is connected as a part of the network that is the internet. And we might connect to the internet using wired or wireless devices. So we've got Ethernet cables, optical fiber in there. Just give me a pointer. You've got a wireless network interface card, a router, and a wireless router there as well, or a wireless access point. And these create local area and wide area networks. And our college is a local area network because it's not over a large geographical area. It's relatively small in the same place. A wide area network would be an example of the internet. That is a wide area network over vast geographical spaces. Also, we've got things like distributed systems. So we might have client and server systems where all our clients in our college would connect to a central server, and that's easy to maintain and manage. Most people will have peer-to-peer networks. So that's where you are your own computer on your own network, and you could do things like seeding and leeching, which is file transfers, and the old BitTorrents and Pirate Bay and things like that. That's used to transfer data files like that, but it's not as popular anymore. So if you get asked about networking standards, you need to be talking about protocols, and protocols underpin all communication. They are necessary. They govern what we can do on the internet. And it's important that we've got standards so that we can communicate to any country or any person. And you've got things like linking a printer to a computer, you need protocols for that, or drivers, linking mobile phones by Bluetooth, and you've got things like FTP, HTTP, SMTP, VoIP or POP3, and that's transferring data between devices and mail and things like that. Email, that is. So what you need to do is you need to have memorized these protocols. File transfer protocol transfers large files over a network. You've got simple mail transfer protocol. Sorry, you've got HTTP. I'm getting ahead of myself. HTTP allows the transfer of multimedia web pages over the internet. So you might have heard of HTTPS. You've also got SMTP, which allows emails to be sent over the network. You've got Internet Message Access Protocol, another mail protocol, but this allows emails to be transferred between computer systems via the internet. And then you've got Dynamic Host Control Protocol, which makes sure that we don't run out of IP addresses, and it uses a pool of IP addresses to choose from. And as soon as your device gets chucked off the network or you close your device down, you relinquish your IP address and it goes back so someone else can use it. And that's what DHCP is for, what it does. You've got UDP, which is datagrams. So datagrams is normally visual or audio data across the network with very few error recovery services. Then you've got transmission control or IP. So TCP/IP is basically a stack of different protocols that enable you to communicate with anybody else. And we have to agree on the same stack in order to talk to each other, really. So that might be transferring images, it might be transferring emails, it might just be, I don't know, sending or watching a video online, that kind of stuff. And all that happens, and when we agree our protocols, we use a process called handshaking to do that. So handshaking is the process by which two devices establish their readiness for communicate. And there's a 4 marker that sticks in my brain that caught a lot of students out, and that's the process of handshaking. So you'll have two devices, and device 1 sends something called an SYN, a signal, to device 2. And it's basically asking, I'm device 1, you're device 2, do you want to talk to me? Then device 2 has to send an acknowledgement and says, yeah, I want to talk to you. Do you want to talk to me? So we acknowledge the first signal from computer 1, and then computer 2 has to send its own SYN signal, and then computer computer 1 has got to acknowledge that as well, so it sends an acknowledgement on the last go. So both devices have talked to each other and said, do you want to talk to me? And the other one's replied, yes I do. And now we can begin our transmission because we've agreed our protocols. Now these packets of data that we send between computers, each packet carries the information that will help it get to its destination. And you've got things like the sender's IP address, the intended receiver's address, something that tells the network how many packets the data has been broken up to, the number of packets and the number of that particular packet as well. And sometimes you have something called a parity bit or a checksum, and they are to help with errors. Now normally you get checksums on barcodes, so that's scanning numbers, doing some mathematical calculation and working out whether it's been tampered or changed, and that's what that's for. So think about the hardware involved in this. So something that we don't talk about, we talked about it briefly in the AS specification the first year, the network interface card. You might have seen these. If your computer accepts an Ethernet cable with an RJ45 head on it and it goes into your computer, laptop, etc., or even your PlayStation or Xbox, then it's got a network interface card built into it. And they're responsible for placing packets onto the network cables in the form of electronic signals, or it could be light if you're using something called a GBIC or something like that. But most computers don't have those. Network interface cards produce electronic signals based on the physical protocol being used, and it sends them down, usually an electrical impulse, down an Ethernet cable if it's copper. So you might have the category 5, category 6, or even category 7 now. You could do this process without a cable. So my laptop has a wireless interface card. It also has a network interface card, a WNIC or a NIC itself. And it basically, when you've got a wireless interface card, it just connects to your router somewhere or a wireless access point. And they all have protection on there as well. So routers and stuff will have WEP or WPA. WPA2 is the most secure protocol that we use to judge security at the moment. Although there were some issues with it, it had to be updated. We've got other hardware like a hub. It's quite rare you'll see a hub nowadays really because they're not smart. So a hub allows you to connect a cable to the hub that sends internet traffic, and then anything else connected to the hub on the other side, you could have 10 computers connected to a hub. All those computers will receive all the traffic. So that's 10 computers. Even if those 10 computers didn't ask for the information, they're getting it anyway. And that's a massive waste of bandwidth. So because of that, we move to a switch. A switch is like a smart hub, basically. And it performs routing of packets from one port to another. So if you request data onto the internet, it comes back and it says, yep, someone requested this, it would go directly to my PC because I requested the data. Instead of everybody getting it, only the person that requested it gets the data. Then you've got a router. So the router performs a very similar job to switches. They route packets to the correct port. And like a switch, they have an internal representation of which devices can be found in each port. Every time you add an additional computer to your network, your router will learn about it through the packets it sends, and it'll know where it lives, and it knows its MAC address and things like that when they connect and when they handshake. So routers are used to connect different segments of a local area network together to allow access to the outside network, such as the internet. So it's our bridge really between the internal and the external. All right, that's that chapter done. My goodness, 54 minutes already. My days, right? So let's fire through chapter 2 because people are talking about networks and they were asking me to go through the networks themselves. So what do you need to know? I split this down into the easiest, most digestible way I knew how. You need to know transmission methods, so serial and parallel transmission. So let's talk about those. These cables here, serial cables. Yes, look at all those ports. So serial data transmission, they're sent sequentially or one bit down a cable, one at a time, which is good because everything stays in order, right? However, using single wires, it does reduce cost, but it slows down the speed of transmission. And when you send data sequentially, it's perfect for transmitting over long distances because there's no synchronization issues. So good for long distances, but not great for speed. A parallel transmission is something that you've seen before. A network cable or an Ethernet cable looks like that, has twisted pairs. And in parallel data transmission, multiple bits are sent simultaneously down different wires or channels within the same cable. Data synchronized by a clock, however, can become problematic over longer distances, and sometimes synchronization issues do start to occur. Using parallel wires is more expensive because there's obviously more copper, more production, etc., but they are faster and they are very, very reliable nowadays, especially with modern materials. So serial and parallel are independent of duplex modes, which means you can have different combinations. So you can have serial, you can have full duplex, or you can have parallel simplex as well. And you should remember your duplex modes, which we will talk about. So let's have a look at those. Simplex, half duplex, and full duplex. And that's all you need to know really. You need to know examples of them. So full duplex, data can be transmitted in both directions at the same time. For example, conference phone, audio, or even like a Google Meet or Zoom. That's video and audio at the same time. Half duplex. So there's older walkie-talkies where you've got data can travel in both directions, but only one at a time. So one sender, stop, one receiver, stop, one sender, stop, etc. And then you've got simplex. Simplex is used when you don't have to actually receive any information, you just transmit it. So data can travel in one direction only, like speakers. Audio signals out, speakers produce it. Nothing goes back into the speakers to send back into the computer, does it? No. Now, next one. What about multiplexing and switching? Okay, multiplexing and switching. You've also got packet and circuit switching involved in that as well. So multiplexing is when data transmission speeds can be increased using multiplexing. Multiplexing is a method where you combine multiple independent data sources on one single transmission medium and they all go to one single destination. Well, multiplexing is combining, demultiplexing is extracting that back out. So several data streams are combined on the same wire. And that saves a lot of money, doesn't it? One wire don't require lots. And there's a little picture for you where they all get combined and they all get extracted. So the multiplexer combines them, the demultiplexer splits them apart. So let's talk about switching. Switching is all about giving the packets the choice of the route to take. Smart little packets, that's what we're thinking about. So packets and circuit switching are two methods of sending packets across a network with multiple paths. That means they've got good fault tolerance and they can decide where they want to go. They're independent. Each packet decides its own route based on how heavy the current load is on that route. It can decide to divert. And it's just like me when I travel to work in the morning. I'll look, the motorway is really busy. I'll go on the A roads today, or I'll take a different route, etc. And that is good because if we bring down one route, then the packet can automatically decide where it needs to go to get there. And that means communication isn't broken. Packets might not arrive in order though, because they've taken different routes, they take different times, so a little bit extra processing has to happen so we can recombine everything together. Now what about, as packet, what about circuit switching? This is old school. A path across the network is set up in advance and all the packets are sent down the same route. Now that route can't be used while traffic is using it. While that connection has been made, no one else can use it, is what I'm trying to say. This reminds me of the old phones that my mum used to have. She used to contact or ring someone and I couldn't get on the internet and use that network while she was on the phone. So all the packets on arrival are in order, but the circuit is vulnerable. If somebody came and chopped the cable outside, the one cable that we had going to our house, we were absolutely done for. No way. So when a link fails, a new circuit has to be set up before further communication can take place, which would cause issues. Another issue is that bandwidth can be wasted, so that whole cable is taken up by one thing, either a phone call or either me trying to access a website, for example. Right? So there we are. There's a little exam tip for you. When considering questions on packet and circuit switching, you normally have to explain the differences between the two. So think about the order of packets and the processing time, how routes are set up. So, circuit switching is set up initially. It's the same route all the time, whereas packets are independent. How resilient are they for damage or break to the cable? And also, which one uses more bandwidth? Okay, there's typical exam questions for A-level. You can pause it and have a go. And there's some mark scheme. Now, last bit now. Typical contents of a packet, which we talked about briefly before. What happens in a network collision and how do you calculate routing costs? It's interesting. So, contents of a packet. Contents of a packet. Inside there, you'll have two different types of data. You've got something called control information and you've got the actual data itself. Now, the control information provides data needed for the network to deliver the actual data. So source address, the destination address, the order number of the packet, the control signals, and the error control bits are all involved in the control information. All right. Now that's normally found in the packet's header or the trailer, which is the back part of the packet. And then you've also, all that information there would be worth marks in an exam. So it's definitely worthwhile knowing the contents of a TCP/IP packet. Each packet of data has that information, so it can help with finding its location or being tracked and needing to be resent or returned. Then we talk about network collisions. Whatever you do, please don't say that a network collision is when data is hitting each other or there's a collision on a cable. A collision is just when two sets of data are detected simultaneously on a transmission medium. They don't even have to touch. They're just detected on a transmission medium at the same time. Now, two transmitted packets, the transmitted packets here, the two packets that we've got, they're discarded when a collision is detected. And what we do is we wait a short and random amount of time before attempting to send the discarded packet again. So why do we wait a short random amount of time? Well, if we wait a short same amount of time, they're going to collide again. So we wait random times, which means they get sent at different times, therefore improving the chances of it getting through. Then, what about routing traffic on a network and calculating the routing cost? So when data is transferred over a network, it's a process called routing. We need to know how long that's going to take. And each route has what we call a routing table, and that stores the different paths along in which the data can be sent. Now the tables get constructed in a memory component like a router, a switch, could even be a firewall or a gateway, and they hold information about routing, so they know the fastest places to send your data. And if it doesn't know, it just sends it to the data exchange anyway. So forwarding tables, there you go, as a forwarding table. So you might be asked in the exam to produce a forwarding table for a node by calculating the lowest cost route on the network. And this is not like Dijkstra's algorithm, people. Literally, all you've got to do is calculate the costs of getting to all the different nodes. So for example, how much is it going to cost to get from A to B? Cost from A to B, anyone? It's 5. Why? Because from A to B, the fastest way to get there is not by this route here, it's via C up here, and that's for a cost of 5. So that's where we would send it, wouldn't we? What about from A to C then? A to C, the fastest way to get there is straight across. What about from A to D? A to D, it's going to go for a cost of 7, so we go here and then up here. We wouldn't go 3, 5 plus 7, would we? No, we wouldn't. All right. What about from A to E? You would probably go 3 to 4 for a cost of 7 and then 4 for a cost of 11 in total. And that's all you've got to do. That is all you've got to do. You've just got to look and add the numbers up to find the fastest route. And you wouldn't get given a large graph to calculate, so you're all good. And this end column here, if you're wondering what that is the first node that you go to. Why do we give you the first node? Because when we send our packet of data, we arrive at the second node, and that is most likely going to be some kind of router. And the router will contain its own table with its own data so that you can carry on to the next one. And that's a routing table right there, people. So finishing this off now, what is bandwidth and what is bit rate? So bandwidth means the amount of data that can be sent from one point to another in a certain period of time. And it's measured as a bit rate. And bit rate is the number of bits that are conveyed or processed per minute of time. So the bit rate is quantified using bits per second, often in conjunction with a prefix like kilobit, megabit, gigabit, terabit, etc. Right? Normally you're sold on the sort of bandwidth route by an ISP, an internet service provider. And the way I think of a bandwidth is pipes. If you've got a really small pipe, a really thin pipe, you're not going to be able to fit much water down it. If you've got a huge, really wide diameter pipe, you're going to be able to fit loads of traffic down there. And if you're looking at the screen there, you can see that 2 lanes, you've got data moving there. But when it gets busy, you probably want 4 lanes, 5 lanes, 6 lanes. So that allows more packets through over a period of time. So that's got a bigger bandwidth. So data transfer rates are measured in bits per second, kilobits per second, megabits per second, and so on. So note bits, not bytes. So if you determine the transfer rate of a 50 gigabyte file that took 2 minutes to receive, you would follow the following steps. You convert bytes to bits. So you know how many bits in a byte? How many bits in a byte? 8. And you convert from minutes to seconds and divide, and the bits divided by the second gives you 3.3 gigabits per second. Okay? Unlikely that you get asked to do that kind of calculation. They give you some context before they do that. So we talked about the internet, we talked about the World Wide Web, and that is us done for that section. Okay? Now, what people ask me for, I won't go through the whole of binary stuff, but it's worthwhile knowing. I know what people always struggle on this. Some people have asked me, I've done those 2 now, some people have asked me for floating point form. Okay? Floating point form. So we're going to do an exam question together. Now binary is definitely going to be on the paper. It might be hexadecimal, it might be base 10, base 16, or base 2. And we've got mantissa and exponent questions. And I've been through quite a few of these because I don't normally teach this during the year. But I've been through quite a few of these with our classes. And all we have to do is follow our 4 steps to complete these questions. And if you do these 4 steps, I guarantee you will get the marks. Okay? So just breathe and take it steady. Read the question. In certain computer systems, real numbers. Real numbers are just floating point numbers. They're stored in floating point form using 20 bits. 20 bits. 16 for the mantissa and 4 for the exponent. Okay? 16 in 2's complement form, which means the first or the most significant bit is a negative number. And in this one, the most significant bit is a negative number. I'll show you that later on. The binary point in the mantissa is immediately after the left bit. That is explaining normalized points. Normalized points. Okay. Convert the number 22.75 to this floating point form. Okay. Step 1, shortest number of bits. 1, 2, 4, 8, 16. Don't need 32, so I take 16. That gives me 4, 5, 6 left. And I'll take 6. Is that 22? Double check. That's 16 plus 4 is 20 plus 2. So that's 22. Then after the decimal point, you have 0.5. You have 0.25. So you half every time. So I've got 0.5 and a 0.75. So that represents 22.75 in the shortest possible bits. That's step 1 complete. Step 2, you then normalize the number. You put a 0 point at the front. And the reason why I put a 0 point at the front is because this number is a positive number. 22.75 is a positive number. If it was negative, I'd have to use this as a 1 here, but it's not in this case. So normalize the number. Then we need to pad out to the required number of bits. So I've got 1, 2, 3, 4, 5, 6, 7, 8. I've got 8 bits, including the normalized point. 8 bits in total. Now I need to get it to 16. So that'll be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So we always pad on the right hand side. I still see people making that mistake. We pad on the right hand side. If you pad on the left hand side, you're shifting the number down and that changes the value of the number, so don't do that. After we've done that now, we need to work out the exponent, and that is the difference between this decimal point and this decimal point. So I've travelled 1, 2, 3, 4, 5 places. 5 places my decimal point, and I have to represent the number 5 using 4 bits. So I can do that now. I can do 1, 2, 4, 8. That's a minus number because it's in 2's complement form. And I've got, I'm representing 5, so it's 1, 0, 1, 0. And if I put these numbers together, put my point there. If you leave your point in, it really doesn't matter. 3, 4, 5, 6, 7, 8. Okay, that's my final answer, and that's all the marks there. So step 1, convert the number in the smallest number of bits. Step 2, put a 0 point at the front to normalize for positive numbers. And then step 3, pad to the required number of bits for the mantissa that's provided in the question. Step 4, then work out the difference between your first decimal point and your second one. And that's it, people. Simple as that. This one here, a little bit more confusing, but we can still do it. It's still fine. Yeah, 23.125. Go back. 23.125. Where's my pen? Yeah, 1, 2, 4, 8, 16. So one of those, none of those. That's 23.5, 0.25, 0.125. So I need none of those, one of those. So that's the smallest number of bits. Normalize that number. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 there. I need 12 bits. 9, 10, 11, 12. Pad on the right. How many decimal points? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Yeah, 5. I've got 4 bits to represent 5. That's 0, 1, 0, 1. Okay, and that's it. Done. 2 marks. Simple as that, people. Just be careful because these are golden marks that you're going to bank in your exam. Okay. So you might get something like this as well. Oh my goodness, look at this. So you can have a go at some of those, especially, there's an interesting one down there, right? Ooh. This one is quite interesting. Right? You just got to go past 0.125 and go again. It gives you that information there. Something like this is where I usually see mistakes happen. Convert the hexadecimal numbers minus 1, 6, 16 and 1A 16 into 2 8-bit binary numbers using 2's complementation and calculate the binary number that would result from their addition. Oh my goodness. Oh my goodness. Right, firstly, just breathe, right? 1, 6. What is 1 and what is 6? Right? Remember, binary uses binary. Hexadecimal uses nibbles. Okay? 0, 0, 0, 1. That's 1. 6 is 0, 1, 1, 0. Right? All we have to do is get this into 2's complement form. That is currently positive 1, 6. We need negative 1, 6. So you use 2's complement to do that. So we go up to and including the first one. So we've taken those. then we invert everything else. 0, so that 1 goes to a 0. That 0 goes to a 1. That 1 goes to a 0. And then all these 3 zeros all become 1s. Negative 1, 6. Oh, John, you're on fire, my friend. Let's do 0, 0, 0, 1. So that's 1. And A, what the hell is A? Well, A is the first number, so we get to 9 in hexadecimal, and then A starts at 10. So 1, 2, 4, and 8 is 1, 0, 1, 0. So that's 10, okay? And that's A. B is 11, C is 12, and so on and so forth, until you get to F at 15, all right? And all I need to do now is, I've done that, I've converted them, 8-bit numbers, yes, 2 complement, calculate the binary number that would result from their addition. So all I'll do now is I'll put 1A under here so we can see it clearly. So 0, 0, 0, 1, 1, 0, 1, 0. Put a line underneath it. 0 and 0 adds up to 0. 1 and 1, 0 carry the 1. Now you must write your carry bits down because you will get marks for them. Don't just leave them out. 0, but there's a carry bit of a 1, so I'll put 1 there. Well, that looks bad, doesn't it? 1 and 1 is 0 carry the 1. 0, 1, 1 is 0 carry the 1. 0 carry the 1. 0 carry the 1. 0 carry the 1. And 1 here, that gets overflowed. Now, all I need to do is work out what that binary number is. Well, 8 bits, I've got 1, 2, and 4. Oh, that's it, it's 4. 4 in base 10. Happy days. Okay. If you've got questions about that, write me an email because it's not live. Huh. Okay. All good? Now what I will do is I will put the mark scheme on for you so you can have a go at those yourself. And one thing I want us to do before we move on to this is I just want us... Have I not got no truncation and rounding in there? Now these advantages and disadvantages, they usually come up in your exam. I see these quite often, definitely in the AS. I see them all the time. So advantages of representing numbers in integer, that's whole number, and floating point form, that's decimal, right? So by decimal I mean it's got a decimal point. Integers, they are stored completely accurately. There's no truncation potentially if I haven't got the right number of bits, etc. But less storage space is needed. Right, so that's good. There's no need to calculate the value before processing, whereas floating point form, right? Floating point has a greater range of positive and negative values. That is better than integers, right? And they're stored in the same number of bits, and also fractions can be stored. But please do not put down accuracy, right? Integers are stored completely accurately. They're more accurate than floating point numbers. You might say, well, the number is more accurate, all right, to what it's supposed to be representing, but you've got to think about it, not in all cases. Right? Disadvantages, fractions cannot be stored, not really for large numbers. You might need more space. Floating point forms are not normally stored completely accurately. Requires more complex processing. There's no exact representation of 0, and by that, what it means is if you've got let's say a sign and magnitude number, and I put 0, 0, 0, 0, 0, 0, 0, 0, and I was like, well, sign and magnitude, that's plus or minus. What if you just give me that number and then you give me that number? What's that? You're having positive 0 and negative 0. What are you doing? Crazy. So that's why it's strange. Okay. So, truncation. Truncation and rounding, you will be expected to compare these. They don't give it on their own. You'll be expected to compare them. All right. Now, for example, if you're truncating, you're chopping the number. So in this example, we've got 8 bits here, and we're trying to chop down and chop these off here. Now you need to work out whether that's going to make a serious issue in regards to the accuracy of your number. And to do that, to prove it, you're going to have to produce something called an absolute and a relative error. An absolute error is the original number, so that's this number here, minus the truncated number here. And what difference does that give you? Once you've calculated the absolute error, you can then calculate the relative error, and that is the result of the absolute error divided by the original number, and that'll give you a percentage. If you do that for your truncated number and your rounded number, so in binary when you round, okay, if I chop off at the same point, if this number here is a 1, then this number here will be changed to a 1. If that number is 0, then that number is going to be 0. Okay? It tries to keep the previous or the after bit, as we say. It's not like we get to 5 and if it's 5 or above, then we keep it. This is, if it's a 1, we keep it. If it's a 0, we don't. And you'll do the same thing again. You'll calculate the absolute error by taking the original number minus the rounded number, and that'll allow you to calculate the relative error by the original error and divided by the original number, and that's 6.7. So which one is more accurate? 28.9 accuracy or 6.7? Well, 6.7 is closer to 0. The closer to 0 you are, the more accurate to the original number your answer is. So the lower the number, the better. And in this case, truncation is rubbish, rounding is better. Now, what about shift functions? We have a logical shift. So you take a register of all your binary numbers, like this, right? And you can do a 1 left logical shift, right? Logical shifts are easy. A logical shift operates and shifts each binary digit left, and the vacated bits are just replaced with 0. So if you shift everything to the left, that 0 pops off, so that 0's here now, which gets disregarded. And whatever moves up, so that one goes to there, and that one goes to there, and that one goes to there, and that one goes to there. The new bit is a 0 in a logical shift. All right? Two left logical shifts, 2 zeros. Right? Now that isn't always completely accurate. We normally try and use an arithmetic shift, and that is a shift that's performed to the left. When the bit gets vacated, if the bit that left it was a 0, you replace it with a 0. If it's a 1, you replace it with a 1. Arithmetic shifts, there you go, same value bit. Now, why do we do the same value bit here? Because that might be a sign bit. If I shifted it like this, and this was a 1, and it was a sign and magnitude number, right, and I shifted it and replaced it for a 0, you've reversed it from a positive number to a negative number. And that's a very, very bad thing. Okay, very bad thing. So when we shift to the right, we always replace it with whatever the sign bit was. So if it was a 1, it's a 1. If it's a 0, it's a 0. Okay? Overflow, you've used it before. Overflow's at the end and underflow is at the opposite end. So there's underflow for you. Now if it's outside the bounds, then you leave it alone. So you just get rid of it. Okay? And that's it, people. That's all the binary stuff for now. Okay, so let's talk about some files then. So in this section, we've got lots of different types of files, but firstly, what is a file? A file is a collection of related records, and a record is a collection of related fields. Or you could say a file is a collection of related data that gets handled as a single unit. So the name of that single unit is, I don't know, names.txt, for example. That's the single unit. Now, what we do is we have fixed length records, which are fixed in their length, so each data type has a certain size, and we restrict how many characters we can put in that data type, for example. And that means we know exactly how big a single record is, and then we take the length of our file and divide it by the number of records. That tells us exactly how many records we've got in our file. Now normally we state the size that we're going to need up front, but we're going to have to be realistic in here because we've got things like our integers coming with different types. We've got signed and unsigned, so we need to be flexible with our size of our files. Sometimes they can't always be fixed. So on the screen there, you'll see an example of us and the size of our file and how we calculate that. But realistically, what I want to talk about is what files do we actually use, and the first one is a serial file, and that's the most straightforward of all our files. A serial file basically just gets data appended to it, and when we say append, we mean adding data to the end of the file, and all the records are stored in chronological order. So that means the time ordered, so the time they arrived is the time that they get stored, is the place that they get stored. So it's important to ensure that the files, when we deal with them, are always open in append mode, and then that forces any subsequent files to appear at the end of the file. So you know that the first record in there is the earliest and the back record is the latest addition to our file. Now serial files, they tend to be used for situations that don't require any order, and the number of records is usually quite small, and the data must be stored in the order that it gets arrived. So sometimes you might see in the exam that they use a reference to things like races, running races, swimming races and stuff like that. They would make use of a serial file. Then we've got our second type of file. This is a sequential or an indexed sequential file. So sequential means sequence, in order. So things are stored in order. Here you've got the index of a book, and that is an indexed sequential file because all of the entries are all in order, but they are also grouped. And here they're grouped by a letter, which speeds up searching, doesn't it? If I ask you to find something in a textbook, you would then navigate to the index, look up the name of the thing, by databases. You'd go D for databases, and you go straight to that section, and then you would search for the databases in that section, which is a lot quicker. So sequential files will all make use of records that have primary key fields which are unique, and one field in the fixed length record gets used to order the records, and that could be either ascending or descending order, it doesn't matter. And the sequential file offers a number of advantages over serial files when it comes to searching. And because they're ordered, because sequential files are ordered, you can use things like a binary search over just a standard linear, for example. Sequential files, two things that normally gets asked: how do you insert and how do you delete from a sequential file? So when you insert into a serial file, you just append it, don't you? Sequential files are much more complex. So what we need to do is we need to add a record, we need to find the position in the file where the record must be added, and then we have to think about moving the records around to put it in there. And in order to do that, we need to create a temporary file to move things around. So let's nail this process then. So when inserting records, they get copied from the original file to the new temporary file. So you copy all the records over one by one into a temporary file until the point of insertion gets found. When that point of insertion is found, you put in your new record, and then you will copy across all the old records from the old file into your new temporary file. So that means in your temporary file now, you've got all your data plus the new inserted data, and then you've also got the rest of the data as well. So you've still got your ordered file. And the only thing you need to do is you then get your temporary file, delete your original, rename your temporary file, and then you're good to go. So a similar process happens when deleting. So only instead of adding a new record, the record to be deleted just gets skipped over. It just doesn't get copied across. And that's it. So then when you have an index sequential file, They have an index that makes accessing groups of record much faster for searching purposes, and the index will group the data in logical chunks and store the file location of where the group record begins. And that means when you're searching through an index file, you only have to search for the group of the search item to interrogate further, and that speeds up finding the records quite a lot, actually. But there are some disadvantages. They're not all good index sequential files, because although having an index speeds up the searching, it does make that insertion and deletion an awful lot more challenging and requires a lot more processing. So every time a record gets added or removed, you have to change all the groups, and that can be a right pain sometimes. And that means every index has to get updated as well. So not just the index you're working on, all indexes need to be re-referenced because all the files are shifting if we delete, for example. Now, index sequential files, they provide something that's quite useful, and that's a multi-level index. So having an index can speed up searching by limiting the searches to a group of records. But what if the index is so large that it takes time to first search for the index itself and then find the group of records pointed to by the index? Well, our answer here is that we're going to use another level of indexing known as multi-level indexing. And the idea behind this is, in my car park, if I went to the car park and you just said, my car's in this multi-story car park somewhere, that's not very helpful. If you said to me, in this car park on floor number 3, in the blue zone, in car park space 34 is my car, I'll be able to find it an awful lot faster. And that's the idea behind multi-level indexes. So here is a typical question that we've seen in the A-level paper. Explain the use of multi-level indexes and draw a diagram to demonstrate the operation of a 3-level index. Award 1 mark for each point up to a maximum of 3 here in the mark scheme. Award 1 mark for 3 tables with appropriate labels, and 1 mark for showing the indexes with 3 appropriate arrows, and 1 mark for pointing to the actual data. So an index is used to improve the read access. So that's gathering. Then there is a main that contains the location of the next index. So that passes on to the next index. So it's a pointer. This process may extend to several levels, and the last index contains the physical address of the record itself. So that's the actual data bit down here. So the diagram for that, you've got your main index where you start first, and you're looking in your index location and you find index number 4. That opens a new index, and then you can look for index 47, and that takes you to a new index. That's 3 levels, that level 1, level 2, and level 3. And then you've got your final index is your actual data itself. So the question asks for a 3-level index, and that's what we've produced. We've got the key and we've got the index location. Another example question that you could also get is something like this as well. A 3-level index. So again, we've got 3 levels. So level, oh, okay, no. Give me my pen, please. 3-level index. We've got 1, 2, and 3, and our actual data. A 3-level index sequential file system stores customer records which have a key field value in the range of 00 to 999. Only a few of the possible key field values have currently been allocated to customers. To save memory space, index blocks are only created when required. At present, only the 3 index blocks shown in the diagram have been created. Customer records are stored on disk in data blocks, and each data block may contain up to 10 customer records. Records within any one data block have key field values which differ only in the last digit. So for example, 5470 to 5479 are stored sequentially. Explain how the new customer records of 3892 and 3893 are added to the system, mentioning the creation and linking of any necessary index or data blocks. And then we've got to explain how the computer would access record 3893 at a later date. So let's have a look at the mark scheme then. So the first one, We create a second level index block with entries from 3000 to 3900. We link the pointer from 3000 in the first level index to the start of this block. We create a third level index block with entries 3800 to 3890, and we link the pointer from 3800 in the second level to the start of this block. We create a data block for records 3890 to 3899, store the two records 3892 and 3893 in sequential order in that block. We link the pointer from 3890 in the third level index to the start of the new data block on the disk. So basically what we're doing is we're explaining our way through what they've provided here into our own example. And it's important to point out here that these are in thousands, then they go into hundreds, and then they go into tens. And that's the sequence that you needed to pick up. For the second part of the question, explain how the computer would access records 3893 at a later date. First begin at the first level index for 3000, then go to 3800 on the next level, and then follow the pointer to 3890 to the data block on disk. Okay? Then we would extract the required record from the data block, and you can also accept there from the exam board, follow the pointer from 3890 to the data block on the disk, locate and load the record required. So there are a couple of different types of style questions that you're going to get for indexed sequential multi-level indexing. And that's an example of why it's faster to go through a multi-level index. And then after we've done serial and sequential and index sequential, now what we need to talk about is something called random or direct access files. And these are probably some of the most useful files, I would say. I use these the most. Random access involves this process of jumping. So jumping to a record directly. So think about the searching, there's no need to search one by one anymore. And to do that, you need to find the record's start position in a file without having to probe it in any way. And that means the only information that you need is the data that you are searching for. And that's most likely going to be a primary key. So there's my hashing, there's my hash brown. You need an algorithm in which when a key is given, it will produce the position in a file, and it must produce the same key every time, regardless of what is already in the file. And that algorithm is called a hashing algorithm. Okay, so just to keep this in your mind, and just to reset this in your mind, you have your data, right? My data could be John. Your hashing algorithm can be anything you want. So if my hashing algorithm was really simple and it said, what is the length of John? And it spits out 3. So data goes in. This is my hashing algorithm. It spits out 3, and it means go to index position 3 in your file. So it goes off to your file. It finds number 1, finds number 2, finds number 3. That is where John would be stored, or that's where John needs to be stored in the file. And that's the process. That is it. It's dead simple. Okay? Dead simple. So random and direct access then. Direct access files means that the file is split into blocks, and each block contains a number of fixed records. So I'll draw that for you. There's your block, and in each block you've got a number of different records all in there. So the hashing algorithm generates the start position of the block. So here's the start position and here's the end position. These blocks are conjoined and you'll have lots of different blocks. So here's another start position. All right. Then what you do is the direct access, not random, direct gets you to the start of the block, and then you start to linear search the blocks one by one. So the file has a maximum capacity, and that gets created on the storage device straight away at the start of the program that you're running. Each block starts off with blank data, but then will take space on the hard disk as these records get filled up in each block. And if each record has a size of S and each block contains R number of records, then you can say that S multiplied by R bytes in size will give you the total number of blocks and sizes. That'll give you the total space that you're going to need. So the number of blocks in the file is decided before any data is added to the file, and that's pretty tricky because you don't know how big your system is actually going to get. And if there are only a few blocks, then the chance of having to do a linear search increases. If there are too many blocks, then there'll be lots of space, and that could waste a lot of time due to the blocks being created initially, wasted memory, wasted searching. So you might have blocks. There's 6 blocks there. Each one has 10 records. Each record is 50 bytes in size, and that's 3,000 bytes there. So it's easy to work out. So the more full random access gets, the worse it performs. And usually the thing that triggers something to think about is the load factor, right? So load factor is normally about 50%. So if I fill my blocks up, there's my blocks, here's my records in my block, and I fill all of these up. Once I get past halfway, it starts to become inefficient at this point because I'm doing a lot of searching. And I don't want to do that if I can help it. So the load factor is calculated like so. And that's by dividing the number of records stored by the maximum capacity. And normally we try and keep it below half. All right. So just to recap, a hashing function is the secret to how hashing, random access works. You put data in, it spits out your index position, and you go to that index position in your file and retrieve your record. If you're trying to add data, you put data in, into your hashing algorithm, it spits out an index position of where you should store your data. So the same data is always used. Now you've got a number of different properties as well. You probably won't get asked about these properties, but when you're building hashing algorithms, you need to make sure you follow these rules. You can have a pause and have a look at those, but they're not that important for what you're doing at A-level. This is a typical hashing algorithm. So you might see something like function, string hash, you give it the key, which is the data, and you give it how many blocks you've got. So I've got 6 blocks and my data is John. It will put my John to lowercase, so lowercase J-O-N. Sum equals 0 for each letter in the key. Work out its ASCII value, so work out the ASCII of J, O, and N. Add them all together. I don't know what the ASCII values are. Do that as a loop. And then return the sum of all those modded by the block count. So modulus operator returns the remainder of the division. And that is how your indexes are calculated. And that's just an example hashing function right there, people. And there's an example of actual data going in on that. And you place Bert, this person over here, Bert, place Sally, or place Betty in their positions. So 3, 3, and 0. And you'll notice there, Bert and Sally have gone into the same block and have filled up quite a bit of space. And sometimes that can be known as a collision. Okay. Now, the more collisions you have, the more records that get placed in the same block. That leads to longer linear searches. So there's a couple of different ways to deal with collisions. And the first way is looking at block overflow. So collisions created by hashing functions can lead to more records being stored in a single block. We know that. As each block has a maximum record count, what happens if the block fills up? And there's 2 options here in block overflow. We can create an overflow area, and that gets placed at the back of your file. Or we can create a new file altogether, create more blocks, and spread the data out even more. But that's the worst case scenario. We don't want to rehash every record. So there's a comparison for you. Realistically, you want to create an overflow because it's the lowest in terms of cost. Searching through the block, the end block, is painful, but if there's not that many data items, then you should be okay. You should be okay. Whereas if you had to create a new file and reblock everything and then rehash all the data, that is a large amount of processing. That is awful. You don't want to do it, people. So we've got a couple of different types of methods. So you've got progressive overflow, and if the location is occupied next to the available location, if the end of the file is reached, we wrap around and start searching from the beginning again. So we might go through our block again, looking for new spaces that get freed up, etc. If not, we just keep looping around, and that can be a bit of a waste of time. Or we can flag the block. So flag the original block and move data to the designated overflow area for subsequent linear search. So what we mean by that is if I have my block here, there's data inside, data inside, data inside, data inside. I've got data in here, data in here, data in here, data in here. I'm full at this point. I'm full. You come along with your data and you go in there, go in there, go in there, go in there. Oh no, we're full. So you'll add a flag onto it and you would have your overflow at the end of your file and you would place it anywhere in the overflow. So when next time you come along looking for it, you'll come along all of your records, you'll see the flag and go, well, I didn't find it, and there's a flag, we must go to the overflow and start searching there. And that's what the flag's for. All right. Now also, in addition to this, master and transaction files, I did have this on my form to cover because people wanted me to, but master and transaction files are files. So that's why we cover them here in this section, and they're also in our modes of operation. So we're covering master and transaction files in as a part of batch files as well, okay, or batch processes, should I say. So some files contain vast amounts of information. So like your phone, for example, how many phone calls are made every day? Millions. So that not only storing somewhere. They need to store information about all the phone calls you've made, and they do that in a master file which contains everything. But I've been with my phone company now for about 15 years, so that's a lot of data on my calls saved. So instead of having all that in one file, we separate it up. And we do that because inserting and updating takes ages to do. And the more data in there, the longer it's going to take. So we have one file to store day-to-day interactions, or week-to-week, or month-to-month, and they're called transaction files. We can have one to store all the data, and that's called a master file. So transaction files store day-to-day data collected over a short amount of time, for example, the current month, and although the amount of data that it produces is still large, it's nowhere near the scale of storing everything forever. And that's what the master file's for. So at the end of the short time period where end of the month you have to pay your bill, we use the data in the file, we pay your bill, and then we port that data from the transaction file into the master file. So we use the master file as an archive. So master files store all the data required to perform batch processing operations, and they also get used to perform data mining. So we can go back in there, mine the data, and find what trends and patterns you use for your spending and things like that. Master files will not be used day to day. Sometimes they're used for things like freedom of information requests and stuff like that, but we don't use them unless absolutely necessary. And there's a classic format question that does appear on the A-level papers, and that is drawing the master and transaction file batch process, and that's what it looks like here. Format question, and you have a pen. Yeah, I've got my master file, and these are old magnetic tape symbols. So this used to be a magnetic tape, this used to be a magnetic tape. So you got your sorted transaction file, and it's sorted because it's a serial file, so it's not sorted by primary key, it's sorted chronologically. You have your master file containing everything from ever, and here in the middle you've got your process. And the process is to update by comparing records from each file. You compare things that you've done this month, and you work out the bill, and you have to pay loads of money. And once you've used the data from the transaction file, it's pointless now, so we put that into the master file and append it on there, and we've got an updated master file. If through the batch process that gets set off, a human will press go, It will do millions and millions of different calculations to work out what you need to pay and what you don't need to pay for everyone across the country. Your error file would be produced because if it comes up against a problem and says, I don't know what to compute, I don't know how to do this, instead of blocking and stopping 6 million processes, it skips over and puts it in an error file. Happy days. And there's a master and transaction question. Describe a data processing system which makes use of a master and transaction file system to produce utility bills. Me personally, I would have explained the inputs, outputs and processes. I would have also have drawn my little diagram with my little snails in there. I say snails, the magnetic tapes, but they look like snails, don't they? Process in there. Sort, there's my master file, there's my error log or my error file, and there's my bill production. Yeah, make sure you do your arrows on there as well. And I've done my diagram. Yeah, just label it and make sure it's all written in and all good to go. All right. Now you've got different files like backup files as well. And backup is the process of copying files across to keep a backup, which is a good practice. And we have backup policies, especially in my workplace. So where's the backup going to be stored? What will it be stored on? How often the backup will be taken? And how long the backup's going to be kept for? All right. Now with backups, if you are backing up, it does take some time. There's a trade-off between how often you back up and how long you can keep the backup and how much storage is required. So eventually, no matter how much storage is used, old backups will need to be deleted to make way for new backups. And if you have to back up everything from a bank, and I'm backing up stuff all of the time, to do a full backup of every transaction ever, it's going to take ages. So what we do is we have a modern approach. We have something called the incremental backup. A full backup gets made, which takes quite a lot of time, but then after that, only changes get backed up. So the only changes to the data. If the data's not changed, we don't touch it. Simple as that. All right, so that's a backup. And the other flip side to that is archiving. Okay. So archiving is the process of moving a file to somewhere else. Okay, moving, that's what our master file is really. It's an archive and we use it when we need it, if we ever do need it. And archiving moves data off your storage medium to somewhere else in the background. And inside this chapter as we go through as well, we'll talk about file generations as well. So file generations, we take this for granted. We don't even talk about it very much, but you have different generations of file. Things like you've got, let me get my pen. Okay, you've got grandfather. Your grandfather, you got your father, and you've got your son. Okay, you can have children as well. You can have great grandfathers, etc. But basically, a file generation is just a derivative of something else. And that's it. Simple as that, people. All right. And there's a little summary for you as well, just in case you need any of those points. I've summarized everything for you into one place. I'm just checking what I've done so far. I've done the fetch, decode, execute cycle, file and file types. I've done internet. One thing that I got asked about was internet and intranet. So what is the internet? The internet is the physical part. And well, what is an intranet then? Intranet is specific to an organization or a company, and it's their own mini internet, let's say. And they use it for business purposes, sending documents around, etc., internal email systems and things like that. So there's not a lot to cover in that really, but the intranet, what can it be used for? It's used for controlling what your organization does and controlling what the people are sending backwards and forwards. It's a more secure way of doing things rather than releasing things publicly across the internet and risking that security. You keep everything internal, and people have to bypass an internal firewall, especially if you're working from home and things like that. So intranets, not used as much anymore, but some people are big fans of it still. I've also done little little man assembly language questions, and I've done hub switches and routers, which somebody asked for. And this is the big one. I think this is the big one. Databases. For some reason, everyone seems to struggle with databases. It's like the fear. And this will be on your paper. That's my belief. I think this will be on. They are very popular questions because students can either access them or they can't. Now, we know everything about databases already from our theory concepts. So we've got databases. They are collections of information that get organized. They are accessed, they are managed, and they are updated. And data is organized into rows and columns in tables. And we join those tables up to find relevant information. Data gets updated, it gets expanded, it gets deleted, okay, it gets filtered and cleaned, etc., etc., etc. And you have two types of database. You have a flat file database containing all the information forever, all of it, and you have relational databases. So a flat file database then, let's look at those first. In a flat file database, information is held in a single table. Each column in the table is called an attribute, and each row is called a record, and you can see the table below there. Now, flat file databases are used for very small amounts of data. This one would be fine for a flat file database, but as they get larger and they develop a big problem called data redundancy, and that is the kryptonite for databases. And our job as database administrators is to get rid of it altogether. So data redundancy simply means that lots of data is being replicated. And you can see in the table below, I've got 2 Jim Donaldsons, and that is not a great feeling. So how do we fix flat file databases that have lots of redundancy? And that is using a relational database. So relational databases are multiple tables that are connected together using keys. And that helps us remove repetition, and it also makes things more complex, right? So you've got advantages and disadvantages, but my belief is the advantages massively outweigh the disadvantages. Now, talking about keys, we have 2 types of keys. We've got a primary key and we've got a foreign key. A primary key is a unique identifier, and in your exam, I guarantee you it'll be something ID. It'll be an ID of some kind, because that's what we do as standard. It's an industry standard to use IDs for that. Booking ID, booking reference, etc. That kind of stuff. Primary keys are usually ID numbers, right? Now, primary keys are vital to creating relational databases. Without them, you cannot create relational databases. You also have foreign keys, which are literally primary keys in another table. That's it. Primary keys in another table. So, for example, in our teacher table here, let's get my pen again. There it is. This student ID, are these unique? Well, there's 2 records here, but are they unique? So we've got a primary key here. I'll just put a star for a primary key. And then here, teacher ID is also a primary key. Now, to link these tables together, we need to use a foreign key. So teacher ID is a primary key, but it's not a primary key in the student table. It's a primary key in its own table, in a staff table. So this here is a primary key. So you need to put the primary key in another table. That then becomes a foreign key. So a foreign key is a primary key in another table. Now, the only other key that you might come across is something called a composite key. And that is where you are stuck and you need to combine 2 attributes together to make a unique identifier. Very rare that you get those, but I'm just warning you, you can get them. But normally the exam board sticks to primary and foreign keys only. So now we've got the basics of flat file relational database out the way, and we've talked about redundancy, and we've talked about different keys. We talk about entity relationship modeling, or ERMs. So we've got a number of different relationships. We've got a one-to-one relationship. So one country has one capital city, and one capital city belongs to one country. Simple as that. Nice and straightforward so far. We have a one-to-many relationship. So one teacher can teach many classes, but a class is only taught by one teacher. Yeah, I wish. All right. Then we've got a many-to-many relationship. So many students sit many exams, and many exams are sat by many students. And we do not want this situation, right? Because there's no primary keys here. It becomes a problem, etc. We need to think about how we're going to fix this. If you come across a many-to-many relationship in a diagram, you need to change it. You need to put something called a linking table in between. You don't even need to know why, right? But basically, you need to have one to reduce redundancy. So this is what you're going to do, right? These are the steps. You are going to look at your many-to-many relationship. I need a pen. Give me my pen. There we go. Right. You're going to remove the relationship. Bosh. You're going to insert a third table. Third table. It's going to be a contraction of the names. Student, student, exam, exam. Put them together, and then you're going to add one-to-many relationships. So these relationships here, you flip them. You flip them. Right? So you cut them and flip them. Right? Many, one-to-many, many-to-one. All right? That's it. That's all you got to do. And now in the student exam table, it is a joint table. This will have the foreign key of student. This will have the foreign key of exam, and they will be combined together to make a composite key. Right, there you go. So here, primary key is student ID. Here, primary key is exam ID. Here, you've got foreign key, but together, they make a primary key. Primary key. So they're the different relationships you can have. One-to-many, many-to-one, many-to-many. That's it. Done. Okay. There is another one. Somebody will go, there's a fourth one, John. Yeah, you can have many-to-one or one-to-many. Good for you for pointing that out. Right. Now, we need to get the process of moving from a flat file to a relational database. And that is called normalisation. We go to third normal form at A-level. So that means we start off in first normal form, we get to second normal form, and then we move to third normal form. If it's not in first normal form, oh my goodness, we're going to have to get it there. So this is the recap. Remember these stages, people. In first normal form, each of the records in your table has to have a primary key. Has to. Can you do that? Probably. Data in each cell should be atomic, right? Atomic. Now, atom, single, right? That means in your table structure, with all your rows and your columns, right? Look in each one, there should be one piece of data in each cell, right? So if you've got something like John and Barker, oh, can't spell my own name, Barker, right? If you've got that in one cell, what are you doing? That is not atomic. You need to split it up, you absolute dingbat, right? You've got to split them up. You've got to have name and surname, forename, surname, or something, right? That's not atomic. You have no repeating groups of attributes, okay? No repeating groups of attributes, columns. Then you've got second normal form, you've got no partial dependencies, and I'm going to show you what those partial dependencies are. And in third normal form, you've got no non-key dependencies. That's where data relies on a column that's not a key at all. That's bad. You can't have that. You've got to get rid of it. So we're going to show you here with practical examples on what to do. Are you ready, people? Buckle in. So we've got here a table, right? Breathe for a second, people. We've got a table. That is all. Now, the table here, we need to look at it and decide whether the data is in first normal form. So it says you must check that the data conforms to the criteria below. Each record must have a primary key. Okay, if it doesn't, we have to assign one. So which one would be the primary key? Hopefully you're screaming member ID. Well done you. Are they all unique though? Looking at each column, we do indeed have a unique data in member ID. So that can be used as the designated primary key. If the table doesn't have a unique column or a combination of columns to make something unique, then you need to add one yourself. Most tables usually have an ID field, like a booking ID, for example. Right, that'll be there for you. Right. Second question, is the data in each field, in each column, sorry, is that atomic? So data can be said to be atomic when a column contains a single value that cannot be sensibly divided or subdivided or split. So for example, in the name field, look at the name field, in the example, it's not atomic, right? That's because you can split that up into first name and surname like I did on the previous slide. On the flip side of that, if you look at the course description, that is atomic when it comes to things like having kayaking, right? But tennis and badminton is not atomic because there's two things in the same cell. We can't do that. So we've got to separate them, right? And you could say, well, all right then, in that case, John, what about assessment date? Right? You can split assessment date into day, month, or year, but why would you split the date up? So we leave it alone because it's not sensible. It's not a sensible split, so we leave it alone, right? So the name of the instructor is also not atomic as well because you can see that there's two instructors. You got Sue and Sue R. So we need to first get the names and surnames of the instructors. So we're gonna have to expand that really. We needed more data. Then on the last one, does the data have repeating groups of attributes? So a repeating group of attributes is a set of attributes that appear more than once in a record structure. So sometimes a single attribute gets repeated and it needs to be dealt with. So in this example, there is a repeating group of attributes relating to certificates. So for example, Emily Marr. Find out Emily Marr. Yeah? So she's gained 2 certificates. The group of attributes that are repeated are course code, description and assessment date, fee, instructor and email, which we need to really rename to instructor email really, because it's the instructor's email, not just the email of the person. So when you find repeating groups of attributes, like so, you need to move it into a new table and then remove it from your original table. So when you move the data, you must be able to link it back to the original record. So you need to include a copy of the primary key from the new table, which is a foreign key. So we need to make a foreign key dependency, right? Now, sensibly, you need to split this up. So in this example, take all of the attributes that relate to certificates that a young person has been awarded. So everything that's linked to certificates we need to take out and give each certificate a link to the young person who has gained the certificate so you know who it belongs to. So let's have a look at doing that. Right. Here we go. There we go. There we go. So what we've done is we've taken everything out that relates to certificates. We've got the member ID, we've got the assessment date when they got it, course code, description of their activity, the fee that they paid, the instructor first name and the last name and first name, and the instructor's email. So I've changed some headings, etc. I've got a composite key, which is the member ID, but remember what member ID is. This now is a foreign key, right? Foreign key. This course code here, that is well, it's not unique, is it? Because look, not unique, not unique, not unique. But when we combine it with this and combine it with this, it becomes unique now. So it doesn't matter that we've got duplicates in there, because combined together in the composite, it is unique, right? Then I can say, right, which person is 145543? I know they got a tennis, I know they did some tennis stuff, right? But who are they? So what you do is you find the primary key value, so the foreign key links to the primary key, go into the members table, and you find 145543 is Precious Jones. So you know Precious Jones achieved that certificate for tennis. Okay? And that's how it works. So now my table is in first normal form. Okay? First normal form. Now, we've got to get this table now, these two tables, into second normal form. So we're looking for partial dependencies. So now you've got two tables, we've got the member table and the certificate table, they're both in first normal form. So to be in second normal form, you must first be in first normal form and now have no partial dependencies. So what is a partial dependency then? So these arise when a table, usually when a table's got a composite key like this really, the member table has a primary key that's made up of a single attribute. So it already conforms to second normal form. Okay, so members table already conforms to the rule second normal form, because everything, Emily is reliant on the primary key, Joe is primary key, Abdul and Precious and Jack all on their unique primary keys. There's no duplicated data there. That is crack-a-lacking. We're good, we're happy with that. The problem here is that the certificate table has a composite primary key, so it needs to be looked at further. We need to determine whether any of the non-key fields in the table are dependent on either of the fields that make up the composite key, so it's the primary key for the member ID, or the course code. So does any of this, assessment date, description, the fee, instructor, first name, last name, and email, does that relate to the course code or the member ID? That's what we've got to think about. So if we find, just looking at that there, I'm just thinking, we need to remember that if a dependency is found where a value varies in line with another value. And what I mean by that is, to help you identify these partial dependencies in the certificate table, the attributes that make up the primary key, we need to think about what they are. So the first non-key field for me, let me get rid of these for a second. The first non-key field, let's look at the first non-key field. Right, so this one we said is a foreign key, and this is a primary key that's linking with this one. All right, now it's not primary because it's just an attribute, so it's not even primary, but it's a key of some, we're using it as a key. Okay, so let's look at assessment date first. This is dependent on the whole composite key, so that's both columns. So it's the date that a specific member was assessed and for a specific course was awarded. So the member sat the assessment and the course was done on, the course used that assessment date. So they're both, this is reliant on the member and the course. That, we need to think about that a little bit further. All right? So leave that for a second. Description, this is dependent on the course code. So whenever you see the code CR0001, you will find the description kayaking. So this one, kayaking. This one, kayaking. There is no more kayaking. If you look at swimming, swimming has the same code. Swimming, anywhere else? No. Badminton, CR0020. Badminton anywhere else? No. What about tennis? Tennis the same, tennis the same. Judo, same, judo, same. Judo L2, different. Okay? So, right. So that means this is dependent on that. Okay? So now, let's have a look at fee. So go through fee, right? This is also dependent on the course code only, because wherever it says tennis, it's always 30, right? Badminton's always 20. Kayaking's always 100, that kind of stuff. So what about instructor last name? So that's dependent on just the course code. So it's dependent on the course code because we need to know the instructor that taught the course. So it's the person, it's the instructor who assessed a specific member for a specific award. So that means that the member is also, okay, yeah, so it's also on member ID as well, because the instructor taught the member and the instructor is assigned to a course. Right, say that again. The instructor taught the member. So we know that Precious Jones was taught by James. Then 22110, who's not in my table, don't know who that is. They were taught by Sue, right? Other people like Joe. Joe was taught by, I can't even say that name, Greta Gause, right? So that means they are dependent on the member ID and the course code. So instructor first name and instructor email, they'd all go together. So that means, cutting a long story short, that is also dependent on the course code and that is also dependent on the member ID. Course code, member ID. Okay. So what I would do is I would look at this and I would go, right, the course code here, the course, if I take out and add a course table, and in my course table, my pen gone again? No. My course table, what could I take out? I could have a primary key. That was the course code. Right? Course code. Then what goes with it? So what's dependent on just the course code? Well, the description is dependent just on that. Description. And I said the fee was just dependent on that, so I'd have fee there as well. Right, description, course code, and fee. Happy days. Now, if I took those out, then all that would be left was the assessment date, the instructor last name, first name, and the instructor email. So let me clean this up for you and show you what that looks like when we break it up. Okay? So remember, before I had my composite key, I've taken out now the course code, so that's gone into courses. My description and my fee have been taken out. Members have stayed exactly the same. Course code is now the primary key. And look, are there any duplicates? No. This is now in second normal form. This was already in second normal form. And now we look at this. And we now need to look at our next table, our certificate table, a little bit further. So just to recap then, now we've moved into a course table. The two fields that had a partial key dependency, so description and fee, were not dependent on both the member ID and course code. So they were partially dependent and they had to go. Okay? You can only keep them in the table if they are fully dependent on both parts of the composite key. In layman's terms, all you have to do is use your common sense to split it up. I'd have courses, I'd have members, I'd have certificates. Right? So, the table will still need to be linked. So I've used course code as the primary key, and now in my certificates table I've got course code as a foreign key there now. So over here I've got course code as a foreign key, membership ID as a foreign key, and together they make a composite key. And we are now in second normal form, yeah, because there's nothing in this table that is partially dependent anymore. So that is also in second normal form. Now then, the last one. Hopefully you're with me so far. Hopefully you are with me so far. So for data to be in third normal form, there must be no non-key dependencies. And you've already been introduced to the idea of a dependency in our partial dependencies before. So now you're looking for any data that depends on the fields that are not designated a primary key or part of a primary key. Right, we'll show you an example of this. So you need to consider all three tables for non-key dependencies. And you can see here, I've built an instructor table, okay? Because using my common sense, I'm looking at this going, right, I've got assessment dates in there. Well, okay, the assessment, we have which courses are being assessed and which members being assessed on that course. So that has to stay. However, instructor, first name, last name, and in email, they are all related under the same topic of the instructor. And that's why I've created the instructor table. The problem is, if I take that data out, how can I make sure that it's got a primary key? Well, I have to make one. And then once I've made one, how do I link the instructor to the certificates table? Well, over here now, that's going to be a foreign key. So I could say to you, in this table, which member is 145543? And you would go, that person is Precious Jones. And what course did they do? DG0011. Go to the courses table. They did tennis for £30. Okay, they got assessed on the 21st of the 2nd, 2019. And who did they get assessed by? They got assessed by Instructor 1, who is Sue James. And you can email her on sue.james@example.org. Yeah? So everything is now linked together. So if you take a look at the member table in second normal form, it turns out that that table is already in third normal form because all the fields, each one of the fields, are fully dependent on the primary key member ID. So that's the first name, the last name, and the phone is all dependent on the member ID key. Lost my pen again. Here we go. So it's all, that one is dependent on that, that one is dependent on that, that one is dependent on that. All dependent. Okay? Next up, we've got the, which one should we look at? What about the courses table then? Right? It's in second normal form. It's also in third normal form. Because, again, all the fields are fully dependent on the course code. So we need to know which course, what the course code is. No, go back. We need to know what the course code is. And we know that the course code, if it's tennis, then you're going to pay £30. So that is all dependent on the course code. Now we've got a certificate table. Okay, certificates. If we do look at that up here, it's not great, right? When we look at it in second normal form, oh dear, what do we have here? So the trick here, in my opinion, if you're looking at that from like at the outside view, right, you need to infer, can you have any more tables from it, right? Is anything still dependent when it isn't a primary or foreign key? Well, yeah, we've got one non-key dependency, and that's the instructor's first name and last name. What is it actually dependent on, right? What is the email dependent on? So for example, Sue James always has the email sue.james@example.org. So to fix that, we built a new instructors table, and all we did is we created a primary key field for it. So most people would probably go with the instructor's email as the primary key here, but I like to have numbers because some people will try and have the same email potentially in the future. So it just doesn't look right. I like a primary key ID, so I'll give it 1, 2, 3, 4, 5, and it looks fine. It looks fine, it works fine, etc. So you've got to ask yourself the question, is it possible for two records in the database to have the same value? If it does, then you need to make it unique, and that's why I use numbers. All right? So there we go. That's my tables all fully built, and that is now third normal form. So just to recap for you, if you're stuck in the exam, you need to get to first normal form, eliminate duplicate columns, get rid of any groups and repeated data, identify the primary key, and separate out any attributes which are not atomic into separate attributes. Check data is already in first normal form, remove any partial dependencies, fix any many-to-many relationships you discover, and check that the data is already in second normal form, and then check there's no non-key dependencies. By that, see if you can split the tables down any further by logic. All right. And that's that for normalisation. Now, we've been studying SQL, hopefully, have we? Yeah. SQL is been around forever. It's just been such a long time. We can insert, delete, create, set permissions, drop tables, whatever. These are exam board examples of what to do. So, for example, you've got select star from students. For me, realistically, you need to get comfortable with the structure. And when you write SQL, I would say that it's important to use keywords in capital letters. It's not essential, but it helps you distinguish select from where, right? Now, how difficult does it get? Well, yes, select from wheres are very simple, worth a mark each, for example, like that. Insert into is a bit more of a complex command. That'll be worth 2 marks. So you're going to insert into the student table, student ID, student name, date of birth, gender, and postcode, and the values are ST9 Adam, etc., etc. So you have to provide, insert into students, provide the names of the fields, the columns you've got there, and then the values are below in speech marks. Okay. Update, so editing, and you can also edit with a where command. So you can update the students table where you can set the student name to Joseph, where the student ID is ST6. So you don't even need the same column data to change another column, if that makes sense. You got delete from the student table where the student name equals Joseph, and that deletes every record of Joseph, by the way. And then really I put this in because this is what you're going to be expected to do as an A-level student, a subselect command. So where there are multiple tables with linked fields like primary key and foreign keys, you will sometimes be asked to output fields from both tables. So you've got your forest block table and your activity table. So this requires a select function with another select function, and that's a linked field. So it's sometimes called a join. You can do an actual join here, people, but that goes a bit beyond the scope. You can do an inner join if you wanted to, but stick to subselect commands because it will work just the same. So for example, showing activity descriptions and start dates of all activities taking place at Little Sutton would look like this. Select activity description, right? So I'm going to highlight what I'm selecting. So select activity description, start date, from activity, that's the table, where block ID, so block ID is this one, right? And this is a foreign key, and block ID here is a primary key. So where the block ID equals, and now you start your subselect command. So this is your subselect command here, right? Then we start a completely new SQL statement. Select the block ID from forest block. So it's block ID from forest block where the location is Little Sutton. So Little Sutton, that means block ID 108 and block ID 196, right? Then, so that means what's returned is 108 and 196. Then it says select the activity description, start date and activity where the block ID is 108 and 196. So 108 gives you this one, 108 gives you this one, 196 gives you this one. That means that felling 3rd of March 2019, planting 09 September 2019, and drainage work 196 22nd of October 2019. Only those 3 are going to be outputted. It's a very specific command that, and they're worth the most marks. Worth bearing in mind. All right. You can drop tables. You can create tables from SQL, which gets a little bit tricky. And you'll notice in here that it says create a table called parents. Parent ID, so that's the first column, has a variable character of 4. So that can be 1, 2, 3, 4, and it's not null. When you put not null in, usually that means it's a primary key because you can't leave it blank. Parent name, varchar 20, not null. Again, you have to fill it with something. Date of birth is a date. And then here, we're told which one is a primary key, and I was right. Parent ID is a primary key, because IDs are normally primary keys, aren't they? Okay, now you can enforce referential integrity. If you don't know what that is, you can basically make things happen. So student ID references student ID. So you can force primary keys or tables to have foreign keys. So what I mean by this is, for example, here is a foreign key and this is a primary key. You can make the parent table have a student with a student ID on update cascade. So it updates every time. The primary key is parent ID. You can force this to happen. So this creates a new parent table with a foreign key linking it to the students table. So the on update cascade instruction means that if you update the student ID in the student table, the foreign key in the parent table will automatically update to match. It has to do that in order to keep its integrity. All right. So a couple of questions for you. This is using the W3 Schools online SQL, which is very good. It's an online database and you can write SQL commands and execute them against a table with not much faffing about, which is fantastic. I want you to retrieve all the data for customers and their shippers. What would that be? So what that would be was select star from shippers, customers. So select all from the shippers table and the customers table. Then retrieve all data from the product table, which you're looking at on the screen, whose price is 18. Now you're going to need a where command to do that. So you're going to select all from the products table. So select star from products where price, which is price here, equals 18. Next one, show all of the order IDs and order dates for all customers whose customer ID is 63 and employee ID is 2. So we need a bit more of a where command. So we'd say select order ID, order date. So they're the two attributes that I want to produce from the order table where the customer ID is 63 and I've used a logical operator and there, and employee ID equals 2. All right. So there's a few more here. Add the following details into the customer table. So I'm going to add 92, John Barker, JB, OSFC, Oldham, OL818XU, UK. So insert into customers. So insert into the customer table. The attributes customer ID, customer name, contact name, address, city, postcode, and country. And the values 92, John Barker, JB, OSFC, Oldham, OL81XU, UK. Delete the record you just created. Delete from customers where customer name equals John Barker. And then fix the record. Well, what's wrong with it? To fix it, we need to update the table. So we say update the suppliers table, set city to London because it says Londoner. We need to set it to London. Where the supplier ID, so which one specifically, where the supplier ID equals 1. All right. Then we start to get into the bigger commands. Create a new table called country. It has a primary key field called country ID. It also has a name field, and both fields cannot be left empty, so you need a not null command in there. And you'd say create table country. Country ID is an integer because it's probably a primary key, and it's not null. Then we have name, which is a variable character of 40 characters, and that's not null. And the primary key at the end is country ID as well. Right. Add a record into your new table that you've created. Oh, go back. And that's it. Okay. Delete the whole country table. You can just use drop. So you just whatever the country, the table is called country. So you just drop table and followed by the name. So drop table country. And then I think the last thing we'll talk about now is SQL exam questions. Look at all the marks on offer for that. If you know SQL, this is an absolute gold mine. of question and answers. All right, absolute goldmine. So in here, what are we going to do here? Explain the term foreign key. I'll explain the term foreign key. So a foreign key, where's my pen again? Oh, right. A foreign key is a field in a table that links to a primary key or part of a primary key if it's composite from another table. So I would put there, this is very basic by the way, I'd probably pad this out a little bit more. It's 2 marks, so I would say it's a, oh no, don't start again. It's a primary key in another table, right? And what is it for? That's what you need to do for the second mark. What is it for? It allows to be linked together. Right, linked together, that's it. Okay. And if a database is already in second normal form, describe the step, one step necessary to ensure that it is in third normal form. Right? No, non, key, no non-key dependencies. And sometimes, if you've not heard of the word, we call them transitive dependencies. Okay, or you could say like if you don't know about those words, you could just say, or just ensure that each attribute or field column depends only on the primary key, right? Only on the primary key. 2 tables have already been created in a database using SQL commands. They are students and tutors. Write an SQL command to output the names and the tutor numbers of all the students. Okay, so you would say, what do you want to select first? So you want to output the names on tutor numbers of all students. So the names, right? So you do stu name because you want the student names. STU name. You would also put down tutor numbers. Tut num. Where do you want it from? You could just get it from one table, and that's, no, it's capital, students, right? Or mark, write an SQL command to output the names of the students who have the tutor number, a tutor with the number 378. So you would go select student name again from the student table, or can't spell, from students, and you'd need a where command, where, and then you would specify the tutor number, tut num, equals what's specified in the question, and you would say 378. 378. Okay. Now, if you're writing SQL for real, you'd put semicolons on the end of these, but it's not for real. This is by hand. So write an SQL command to change the tutor number of all those students whose tutor number is currently 378. Their new tutor number should be 345. So when you say change, I'm thinking we need an update command. Update. And you're going to update this into the students table. So update into the students table, and you're going to set the tutor number that's equal to 345 you're going to set that to 345 where tutor number equals 378. So set it to 345 where it's 378. Okay. That'll get Solomon there. 378. Yes. That would those people. Yeah. So right, let's go and change the tutor number of all the students and students comes out here. So change all these because we're doing the students table. Write an SQL command to output the names of all students who have the same tutor as 13777. How on earth are we going to do that? We need to extract the names of all students. We're right. We need a subselect command for this, people, because we're trying to take the names of all the students who have the same tutor. So we need to output the names of the students first, which we can do. We can definitely do that. So select, and you want to output the names of the students from the student table. So stu name from students right, that's the first bit, that's what we're going to get, and then we'll say where, and now we need to rely on the foreign key. So where the tutor number equals, and then we start our subselect command, and we'll say select tutor number. Forgot what it said in the question. Students who have the same tutor as student 13777. So select tutor number from, go down here, from students where people have, where people have the same, yeah, from students where, which one is it? So it's the student number, isn't it? Where the same number is on number equals 13777. What's the bracket? All right. So select student name. So give me the students from the student table where the tutor number is the same as the, where the tutor number is the same as the student number 1377, and that 1377, the tutor number is 307, so it should return all the students with the same. So it return Brown, Walker, Brown and Pang. Walker's the guy we're looking at. Right, 2 markers. These are pretty tricky. These 2 markers. Write an SQL command to output the names of all students and their tutor names. So again, we're gonna, this one's quite interesting because we're gonna need to get this here and also all the students. So we're gonna have to merge 2 together. Right then, so select the student names again. So output the student names, comma, tutor names as well, tut name, from, so we're mushing them together now, from students for the stu name, students, yes, comma, tutors, so both tables are coming in, right, where right, so we've got to match these together. So watch what I do now. Watch what I do. A little bit of magic where students dot, okay, students dot tutor number, are the same, so equals are the same as tutors dot tutenum, right? So this one, tutor numbers here and tutor numbers here, those link together, right? That students.tutor number and equals tutors.tutor number, if them two match, produce the student name and the tutor name of those people. Again, another subselect, but we've not seen the referencing like that before. It's a pretty nifty way to do it. Okay. Write an SQL command to create a new table, phones, oh my goodness, to contain the telephone number of each room. Assume there is only one telephone per room. So, okay, create table phones. So create table phones. They provided that, phones in the question. It was in capitals, they've already provided that. And then it's going to contain the telephone number of each room. Each room. So it's going to be multiple rooms then. So we're going to need room number, and inside that room number is going to be a phone. And it's got a phone number. So I'll probably have two of them attributes there. The phone number, room numbers, I mean, what would you have like? You could give it like a char 3, like room number 1, 2, 3, I don't know. Something practical anyway. And this one, you can have multiple characters. Phone numbers don't need to be numbers, by the way, because you're not using them for arithmetic operations. And the phone numbers, I don't know, I put 5 in there. You might be thinking, why have you not put 11? Because it's like a hotel in it, or a whatever. It's like room. It's like you dial the room number for the phone, so the room number would be the same. Like you dial 1, 2, 3. You dial at work. You dial. I can't remember what my phone number is. Like 3018 or something, and it will go to me. Now, one thing I did forget there: create table phones. You would have a bracket opening there and a bracket closing there, because they're two input commands. Then write an SQL command to enter the following data into the table you have created in part VI. Room 106 should have a telephone number. There you go. Telephone number 625. So I'm probably over-egging the pudding here with 5. Looks like they've got 3 and 3. Maybe I should change that to 3. Yeah, I will. I'll change to 3 now. There you go. Right, so I need to put them in. So I need an insert command. Okay, an insert command. No. Insert into phones. Now, people normally ask me when they do these commands, insert into phones, values, and then you would write 106, do what it does there, and so that's room number first, and the telephone number 625, so I should put 6, 2, and 5. People say to me, can you not just put a comma and have like more, like can I not just add 113 and 670 on the end of that? The answer is no. One insert command per entry, because otherwise they get confused with their attributes and stuff. So insert into phones. It's really hard to write, people. I hope you appreciate my wrist is on fire. This is now 2 hours and 49 minutes of just pure computer science. That's 670. 113. There we go. Bish bash bosh. Awesome. The last one, write an SQL command which will output the names of students and their dates of birth in descending order. SQL command. Names of students and the date of births in descending order. Right, well, I know descending order is like DESC. I know that much. You could say ASC or DSC, I think it is. So what I'll do then is I'll say select, spell it right, select the student name of that person then. Select their date birth. Why is it date of birth? Date birth. How strange. Select date birth from the table students. So from the table students, order by date birth, DESC at the end. That's probably what I would do. And that's it. I mean, to bank that, what's that? 2, 4, 6, 8, 10, 12, 14, 17 marks. What the hell? 17% of the paper right there. If you master that, you're absolutely flying. So let's, I'll put some other questions on the board if you want to have a go at those. On the board. Yeah, okay. On the screen, should I say. There you go. There's some more. And you can pause that and have a go now. I'll put the mark scheme up in just a couple of seconds for you so you can have a look. Okay. There you go. That's worth a bit less, that, but still effective skill nonetheless. Okay. Now, the only thing I've not covered in there is operating systems, I think, but I am absolutely dead. There are videos on operating systems, or if you have want me to go through operating systems, or you want to email me, etc., we can sort something out there and get something sorted. But people, that's a lot of topics that we've done there. Again, apologies for the live stream interruption. I can't help a car driving into a fibre optic box. Virgin Media apologise on their behalf. I'm sure they're gutted about the fact that we couldn't do a live stream. So this is the next best option. Hopefully you found it useful. I will still timestamp these as said, and I wish you the best of luck in your exam that is up and coming. If you need me, you know where I am via email. Good luck and all the best, people. See you on Monday.